In previous videos, we learned about 5 different ways that energy can be stored inside of a system. And then we've learned how to use pie charts as a way of modeling how the energy is stored in a system. But we've been using this word system without defining what system really means. So in this video, we have 2 goals. One is to learn what the word system means, and then secondly, to learn about one of the most fundamental laws in all of science and how a system helps us keep track of it and make use of the law to make predictions. There's a law called the First Law of Thermodynamics. It's one of the most fundamental laws in all of science. It's sometimes called the law of conservation of energy, which is a little bit more descriptive. And the law of conservation of energy really means that energy in the universe is conserved. In other words, there isn't any more of it than there ever was, and there won't ever be any less of it than there is now. Because this is a law, what that means in science is this is something that we have found to be universally sort of true. We've never found an exception to it, and it seems to be a model that really matches how the universe seems to behave. Now, it's impossible to track all the energy in the universe. So we're mostly concerned with changes that happen in little parts of the universe. So we're going to learn about a tool today called the System Schema that allows us to focus on change and divide the universe into pieces so that it's manageable and we can study energy flow into and out of those pieces. So when you think about dividing the universe into 2 pieces, the system and then the rest of the universe that isn't the system, we can read the first law of thermodynamics a different way. We can say that the energy in that system, so it's just a way to make the giant universe a little bit more manageable, so we can apply this first law of thermodynamics, the law of conservation of energy, and make it work for us to make predictions. Let's learn about this by thinking about this event that we saw in a previous video. So this is a person arming a dart gun that's spring-loaded. So the spring gets compressed, then it pushes a dart out, and then the dart flies into the air and will slow down and get higher and higher away from the surface of the earth. We saw that at first all the energy was stored as chemical in the person, and then there was less chemical energy stored as the person armed the spring, and then some elastic energy storage made up for that loss. And then as the spring began to unwind and the dart speeded up, some of the elastic shrunk down as kinetic got larger and the dart was speeding up. And then eventually that's all of it would have been kinetic, but then as the dart starts to fly into the air, gravitational begins to appear and take over the kinetic until eventually the dart will stop moving, kinetic will be 0, and gravitational will be the highest. In this situation, we were tracking what was going on with energy storage in all the involved objects: the dart, the person, the spring, and the Earth. And by Earth, we mean the planet Earth that exerts gravitational pull. So in the system schema, each of the interacting objects has its own little rectangle. So there's the dart, the person, planet Earth, and the spring. And then there are some arrows drawn between these things to represent how these things interact. The person interacts with the spring, so there's an arrow there. The dart interacts with the earth. The spring interacts with the dart for sure. I'm showing that the person is interacting with the dart. I'm not really sure that that's true. But we have a lot of connections between these different objects. And then this is really critical about the system schema. There's this dotted line that goes all the way around the whole works to show that everything involved is included inside the system. So that line is the system boundary. In this case, there's not much of a boundary because all the interacting objects are inside. Now, obviously, these are not all the objects in the universe, but these are all the objects that are involved in these changes. We call this a closed system. So it's not possible during these events for energy to cross the boundary into or out of the system because all the interacting objects are inside that system. Often closed systems are not very interesting. Here's an example of why. The fact that ETM dominates the size of these pies masks the real change that's going on during this event. So it might be smart to redefine our system. Instead of having this closed system with all the interacting objects inside the system, what if we changed it so only the dart, the earth, and the spring were inside the system? This is what we call an open system because it's possible for energy to cross the boundary into the system or out of the system. So now let's take another look with this system schema. this system definition, we'll find that it'll make the changes that are taking place clearer. At first, there is no energy stored in the system, because remember, all of our original energy was ETM. That's stored in the person, and the person is outside the system now. As the person arms the dart, energy crosses the boundary. Energy crosses from person to spring. That crosses the boundary, and that's like depositing the paycheck in your bank account. The pie gets bigger because something came from the outside into the system. So now all the energy is stored as elastic energy in 2, but in 1 there was none because that was all outside the system at that point. The next thing that happens is the spring begins to unwind, and less of the energy is stored as elastic, and more of the energy is stored as kinetic as the dart begins to move. So energy is being transferred from the spring to the dart, but that does not change the size of the pie. And the reason it's not changing the size of the pie is because the spring and the dart are both inside the system. And finally, the spring has lost all of its energy to the dart and the earth. That couple of dart and earth can store gravitational energy. You have to have the earth in there for gravitational energy because it exerts gravity. And so now we've got some EG here and a lot of EK. And then if we had a position 5 here with the dart flying up to the top of its arc and coming to a stop, all of this green EK would have shrunk down to nothing, and the entire pie would be EG. Let's take a look at another schema. This is also going to be an open schema. And now we have only the spring inside the system. So the dart, the earth, and the person are still there because they still exist and they still interact. But this is an open system in which only the spring is present. What would that make our pies look like? Well, first of all, there's no energy stored at 1 because that was all ETM in the person, which is outside the system. Then, as the spring gets armed, energy crosses the boundary from person into spring. So that allows us to store a bunch of E elastic in the spring inside the system. Then the spring begins to unwind and push the dart forward. So the spring is interacting with the dart, passing energy to the dart. That crosses the system boundary, but now the energy is going out across the boundary. So that means the pie is shrinking because the spring is no longer storing as much energy, and the spring is the thing that's inside the system. Finally, in number 4, there's no energy left inside of our system. The energy is still in the universe. It's now stored in the dart-earth couple, but it is no longer in the spring, and that was our system. Let's do one more. Here's another open system, and now only the dart and earth are in the system. Again, this is an open system because there are some things outside the boundary that could transfer energy in or out. So there's different energy tracking again. At first, no energy is stored because it was all ETM, and that's in the person. Then, as the first change happens, as the spring is armed, energy transfers from the person to the spring. But when the energy transfers from the person to the spring, that entire exchange happens outside the system. So at position 2, there's still no energy stored in the system. From 2 to 3, the spring begins to push energy into the dart. So energy now, for the first time, is crossing the system boundary into the dart-earth system. So we start to get a little bit of energy stored as kinetic energy as the dart begins to move. Ultimately, somewhere between 3 and 4, all of the energy crosses from the spring into the dart-earth system across the boundary. And so now we have a full-size pie, but it's split between gravitational and kinetic as the dart is moving, slowing down, and getting higher away from the surface of the Earth. Let's look at another example. Remember this event? So we have the family sliding down the hill. These were the pie charts that we ended up using when we were analyzing this in the first video. But there we were assuming a closed system with the Earth, the sled, and the people all inside the system. This isn't the most interesting way to look at this because remember, ETM doesn't change ever. The family isn't exerting any energy as they go down the hill. All the change is happening with the Earth and the sled. So if we redefine the system so that only Earth and sled are in and the people are out, what would the pie charts look like? Stop the video and see if you can come up with pie charts that would be appropriate for 1, 2, and 3. Well, here's what I find. At first, all the energy is stored as gravitational energy because they're at the top of the hill and the people are outside the system. Next, at position 2, the energy is split between kinetic, because it's moving, and gravitational, which is smaller than the whole entire pie because it's not as high as it used to be. And then finally, at the end, all the energy is stored as kinetic energy because they're at the bottom of the hill, moving fast, and have no gravitational energy anymore. All of the changes here happened inside the Earth sled system. And so the pies are the same size. The people store energy, but it stays outside the system the entire time. System schemas are a really useful way to divide the universe into parts and make it manageable to help us make predictions about how the world is going to behave. In later courses, you may learn how to quantify energy, and the way that we transfer energy across system boundaries, we have ways of knowing that. We have ways of figuring out how much energy is transferred, and that allows us to make really good predictions about the cost of things and also how fast they're going to be moving or what their positions are going to be. It just becomes a really important problem-solving tool for physicists and engineers, chemists, other people who have to make reliable predictions about how the world works.